Yo, 2016 AS Physics Unit 1 paper, question 4. This is your Young's modulus question. It's actually quite a good one because they've given us a full experiment of measuring extension, and then we work out the Young's modulus later by looking at a graph. Sometimes they ask you to describe this experiment. This is a good past paper to look at and study this here, and if you could regurgitate this if they ask you to, you'd get the full marks, right? So try and remember this diagram and this method for determining the Young's modulus of a wire. It does say here the test wire and the reference wire are of the same length and material. Now that's useful because the first question is, explain how the effect of a change in temperature is minimized. And the answer is both the test and the reference wire are made of the same material. So if there was a change in temperature, the amount of extension or retraction would be equal in both, right? So that's what they was looking for there. On to the next page. Bit of note work here. State what is meant by the term elastic limit, and in bold, and explain how the experimenter would know whether or not the test wire is extended beyond its elastic limit. So obviously you've learned this. The elastic limit is the point at which the material will not return to its original length. There's been permanent deformation. To explain how you would know whether or not it has extended beyond it, you would just take off the weights, take off the load, and check that it goes back to the original limit, the original length, or is there an extension implying deformation. State why a long wire is used rather than a short one. Obviously the longer the wire, the more extension will be produced and the easier it will be to measure accurately. And why is the diameter measured at several different places? So then you can work out a mean value, which again improves and increases the accuracy, right? Usually we do it about 5 times. Right, so that's all good stuff. Those easy 6 marks, just pretty much notes out of your folders. Then on to the mathematics part. Here's a graph. It's force versus extension, right? Load in newtons is the weight, which is the force, versus the extension. As you can see, if I don't hang on a weight, there's no extension. It starts at the origin. They give us the original length of the wire in meters, and they give the mean value of the diameter in millimeters, right? So whatever you do, make sure you get everything in the right units, okay? I would recommend sticking with the SI, get everything in meters before you think about doing any button pressing on your calculator. So I would consider this as 0.32 times 10 to the minus 3 meters, okay? Don't forget, we're going to need the radius because we're going to be working out the cross-sectional area, so you'll have to half that. It says, using the graph and these two measurements given, give a value for the Young's modulus, right? Now it does imply it's a metal wire, so we're looking for a power of 10 of about 11. Right, 10 to the 11 is a standard Young's modulus answer for a wire. Obviously different for rubber, which has come up on other papers. So have that in the back of your mind when you start doing the calculations. Young's modulus is stress over strain. Stress is force divided by area. Strain is extension divided by length. So if you're doing stress divided by strain, you obviously flip the second one upside down and multiply. So it's force times original length divided by area multiplied by the extension. So pick in some points on the graph. I've picked, using the top part of the graph, I've picked the force of being 28 newtons. That gives me an extension of 4.8 times 10 to the minus 3 meters. Again, looking at the graph. The original length was 2.4 meters. So the other thing I have to calculate is the area. We assume the cross-sectional area is a circle. That's the diameter, half it to get, oops, sorry, not on camera. That's the diameter, half it to get the radius. So my area is pi times r squared, pi times 0.16 times 10 to the minus 3 squared. Very, very carefully chuck it all in your calculator. Do it a couple of times to check you get the same answer each time. And I've come out with 1.74 times 10 to the 11 pascals. And I'd be happy with that because I was expecting that 10 to the power of 11. The last thing then is calculate the energy stored when it is extended by 2.4 millimeters. The energy stored is the area underneath the force extension graph, right? So you need to go to the extension of 2.4 millimeters, come up, and you've got to find the area underneath that bit of graph there, which is a triangle. So it's of course half the base times the height, half of 2.4 times 10 to the minus 3. Don't forget, it was in millimeters, multiplied by the force, and at 2.4 the force was 14, which gives me an answer of 16.8 times 10 to the minus 3 joules, right? Gotta be honest, I've seen more difficult questions on this topic. That was a good one. Bye-bye.